All right, get ready to dive into some really cool research. Someone sent us this paper, and it's a fascinating one. It's called, get this, PXHELL, When Pixels Learn to Scream. Catchy title, huh? It's by Mordecai Guri from Ben-Gurion University. And the idea is wild. What if your computer screen, like the one you're probably looking at right now, could actually make sounds, not through speakers, but through the pixels themselves?
Yeah, it sounds kind of crazy at first, like something out of a sci-fi movie. But Guri's research actually shows how you can turn an LCD screen into a sort of rudimentary speaker. Basically, he found a way to manipulate those tiny pixels, how they change, to create sound waves.
I bet this is especially interesting in places where you absolutely can't have normal speakers, right?
Exactly. Think about those super secure computer systems, the ones they call air-gapped. They're isolated from any networks, and they often don't even have speakers, like they're totally audio-gapped too for extra security.
So no sound can leak out, carrying secret information.
Right. But Guri's research kind of blows that wide open. He's basically using the screen itself to make the sound, which bypasses all those security measures.
It really makes you think differently about screens, you know? We usually just think of them as for visuals.
Totally. I mean, we see LCD screens everywhere, every day, but how many of us actually know how they work?
It's more complicated than people realize. I mean, there's a backlight, that's for illumination, obviously. Then you've got this layer of liquid crystals. That's what modulates the light coming from the backlight. And then there are polarizers. They control which direction the light's going, so you actually see an image. And it's all very precisely controlled by this whole network of circuits and capacitors. They're what apply the right voltages to each pixel to make it change.
So those electrical signals, the ones controlling the pixels that Guri figured out how to use to make sound.
Precisely. It all comes down to this thing he calls the screaming pixels phenomenon. Basically, when a pixel changes state really quickly, like going from black to white, it causes these tiny vibrations in the screen's capacitors.
Hold on, vibrations. How does that even work?
Well, it's because of something called the piezoelectric effect. I won't get too technical, but essentially certain materials vibrate when you apply an electrical voltage to them.
Huh. Interesting. So those vibrations are happening all the time in our screens.
Yeah, but they're usually way too small for us to hear. But what Guri did was figure out how to amplify those tiny vibrations using specific patterns of pixel changes. And by controlling those changes, he could actually make sound waves that we can hear.
Wow, that's amazing. He's basically turning the whole LCD panel into a kind of speaker, isn't he?
Exactly. It's like he's composing this, I don't know, a visual symphony of pixel transitions to create sound. It's pretty wild.
So how does he actually tell the pixels what to do? Like, how do you translate sound into something a screen can understand?
It's complicated for sure. He had to develop these special algorithms. Basically, he creates these bitmap patterns. They're like visual representations of the sound waves. And displaying those patterns on the screen causes the right kind of vibrations.
So it's not just about what image is on the screen, but how fast and in what order those pixels are changing.
Right. Yeah, exactly. It all ties into something called the pixel clock. That controls how fast the pixels on the screen are updated, and that speed directly affects the frequency of the sound you get. Guri can actually fine-tune the sound by manipulating that pixel clock, which is tied to the screen's resolution and refresh rate. He even used these really simple patterns, just alternating black and white blocks of pixels to create specific frequencies. It's like an on-off signal, like Morse code almost.
This is blowing my mind. We're talking about turning screens into speakers, but I bet it's more than just making noise, right? I mean, you could actually send information this way.
You got it. The sound is just the carrier, really. The breakthrough is that you can embed data within that sound. Guri uses something called frequency shift keying, or FSK for short.
Can you break that down for us? What's FSK all about?
Imagine you've got different sound frequencies. Think of them like different musical notes, maybe. And you assign a specific frequency to represent a 0 and another one for a 1. So by quickly switching between those frequencies in a specific pattern, you can essentially embed a stream of binary data.
So the screen's like a transmitter, sending out secret messages in sound waves. That's incredible.
Exactly. And to make sure that transmission is reliable, Guri developed a simple protocol. It's kind of like how data is sent over a network. You've got packets, each with a preamble to mark the start, a header with information about the packet, the actual data itself, and then a checksum to make sure nothing got corrupted.
It's amazing how he's taking these principles from network communication and applying them to this totally new way of sending data. But I have to ask, does it actually work in real life? Like,
Yeah.
did his experiments actually pan out?
Oh yeah, he did some really thorough testing, tried it with different LCD screens, measured how loud the sound was, how far it could travel, and how accurately the data was received. And it worked, though, with limitations, of course.
What kind of limitations are we talking about?
Well, the sound is still pretty weak, and it doesn't travel very far. You're talking a few meters, max. But he proved the core concept. It definitely works.
So maybe not broadcasting across a room, but enough for short-range communication. That's still a huge deal.
Absolutely. And it's just the beginning, really. This opens up a whole new area of research. There's so much we can explore and improve upon. And what's particularly interesting is that he found the signal strength actually changes depending on the type of screen you use, where the receiver is relative to the screen, and of course the distance between them.
That's fascinating. So many variables to play with. It sounds like there's a ton of potential here. And you know what? We're going to explore that potential and more when we come back after the break. We'll dig into what screaming pixels could mean for everything, from assistive technology to the security landscape. Stay tuned.
Welcome back. So we've been talking about how Guri can make LCD screens actually produce sound. But to really appreciate what he's done, we need to dig into some of the technical nitty-gritty. It's pretty impressive stuff.
Yeah, like we were saying before the break, it's not just about making the pixels light up. It's about making them change in a very precise way to control the frequency of that sound. That's got to be tricky.
It is. And one of the things Guri had to deal with, something a lot of people might not even think about, is something called blanking intervals.
Blanking intervals, what are those?
So every time your screen refreshes, there are these very brief moments, these intervals, where the pixels aren't actually displaying anything. It's like a tiny pause. They're important for how the LCD works internally, but they throw a bit of a wrench in the works when you're trying to control the sound frequency so precisely.
So you can't just take the screen's specs, like the refresh rate, and plug them into a formula, right?
No, not that simple. Guri had to account for those blanking intervals to make sure the frequency was spot on. It's really a testament to how meticulous his research was.
It's amazing how these tiny details can make such a big difference. So let's talk about the data itself. How does he actually encode information into those sound waves he's creating?
Well, he uses a technique called frequency shift keying, or FSK. It's a pretty standard method in digital communications. Basically, you use different frequencies to represent different symbols. In this case, it's the zeros and ones that make up binary data.
So kind of like Morse code, but with different sound frequencies instead of dots and dashes, right?
Exactly. And by switching between those frequencies in a very specific sequence, you can embed a whole stream of binary data within that sound coming from the screen.
That's so clever. But I imagine sending raw bits isn't all that useful. How did Guri actually structure the data to make sure it could be transmitted reliably?
He created a packet-based protocol similar to what's used in network communications. Each packet has a preamble, a header, the payload, and a checksum.
Break it down for us. What do all those pieces do?
Sure. So the preamble, that's like a marker that signals the start of a new packet. The header contains information about the packet itself, things like what type it is or its sequence number. The payload is the actual data you want to send. And the checksum, that's like an error detection code. It makes sure the data hasn't been corrupted during transmission.
So it's like putting the data in a nice little package, all neat and tidy, so it gets where it needs to go without any problems.
Precisely. This packet structure ensures more organized and reliable communication, even though you're using sound waves, which can be a bit finicky, to transmit the data.
Right, because we were talking about limitations earlier. What were some of the challenges Guri ran into when he tested this out in real-world situations?
One of the big ones, and we touched on this before, is range. The sound produced by the screen, even though you can hear it, it's pretty faint. It doesn't travel very far before it becomes too weak to pick up. His experiments showed it worked reliably within a few meters, but beyond that, the signal degraded significantly.
So not exactly broadcasting across a room, then.
Not yet, anyway. But even with that limited range, there are still plenty of potential applications where short-range communication is all you need. And think about it, we're still in the early stages of this technology.
True. It's not like this is a finished product or anything. What about speed? How much data can you actually send with this method?
Well, in his experiments, the data rate was fairly modest. I mean, we're talking a few bits per second. That's partly due to the nature of sound waves themselves. They're not the fastest way to transmit information. And of course, you need error detection and correction to make sure the data gets through intact, and that slows things down a bit.
So we're not streaming movies with screaming pixels just yet.
Well, no, not quite. But this is really just a first step. With more research and refinement, it's totally possible to increase both the range and the data rate.
And it's not all about just pushing those limits, right? It's about finding the right applications, things where the unique strengths of this technology really shine.
Absolutely.
Yeah.
And one of the ideas Guri explored in his paper is using multiple screens simultaneously. He calls it screen splitting.
Multiple screens, huh? How would that work?
So imagine you divide a single display into separate regions, and each region transmits on a slightly different frequency. It's like creating multiple channels all running in parallel, and that could potentially boost the overall data rate.
It's like a choir of screaming pixels, each singing their own part of the message.
That's a great analogy. Of course, there's a trade-off. The more channels you have, the weaker each individual signal becomes. But by carefully tuning those frequencies and figuring out the best screen splitting arrangement, you can strike a balance between speed and reliability.
This is all incredibly exciting. It feels like we're just scratching the surface of what might be possible with this technology.
Mhm.
And, it's not just about the technical stuff either. There are bigger implications here, things we need to consider carefully.
Exactly. We're talking about a whole new way to interact with technology with all sorts of potential benefits, but also potential risks.
And we're going to dive into all of that, the good and the bad, when we come back after the break. We'll be exploring the broader implications of streaming pixels, from its potential to help people to the security challenges it might pose. Stay with us. All right, welcome back for our final look at Screaming Pixels. It's been a wild ride so far, right? We've gone deep into how Guri actually made this work, how he got those pixels to sing, so to speak. But now it's time to step back a bit and think about the bigger picture. What could this technology actually mean for the world?
Yeah, it's really mind-blowing stuff. Guri's research is definitely impressive on a technical level, but I think what's even more exciting is how it makes us rethink our whole relationship with technology, with screens especially. It opens up all these possibilities that could fundamentally change how we interact with the digital world.
Totally. I mean, we're so used to thinking of screens as just visual things, right?
Mhm.
But now we're talking about them actually making sound, transmitting information through sound waves. So it's a whole new dimension has opened up.
And that new dimension could be incredibly powerful, especially for people who have difficulty accessing information through traditional visual means. I'm talking about assistive technologies for the visually impaired, for instance.
That's a great point. Imagine a screen that could literally talk to you, tell you what's on the screen, read out menus, even provide audio cues to help you navigate.
Exactly. Screaming pixels could give visually impaired users so much more independence and control over their digital experience. It could really bridge that gap between the visual and auditory worlds.
It's amazing to think about how technology like this could be used to make the world more inclusive, more accessible to everyone. But the potential goes way beyond assistive technologies, right? What about all those devices we have nowadays, all those smart gadgets that are connected to the internet?
The Internet of Things, yeah, that's a perfect example. So many of these devices, sensors, wearables, even things like your refrigerator, they're connected, but they don't have speakers.
Because who wants a speaker in their fridge, right?
Yeah. Right. But what if your fridge could just use its display to give you a little audio reminder that the milk's about to expire? Or your smartwatch could send you a discrete notification through its screen. Screaming pixels could be a really low-power, low-cost way to add audio to all sorts of devices.
It would be like having a world of tiny whispering screens all around us. Kind of eerie, but also cool in a way. But of course, we have to talk about the potential downsides too. Like, what about security? I know Guri mentioned that in his paper.
Yeah, any new technology, especially something this powerful, comes with potential risks. And one of the big concerns is the possibility of covert channels. That's where an attacker could use this technology to leak sensitive information from a supposedly secure system.
Covert channels, that sounds pretty scary. Can you explain how that would work?
So imagine you've got a computer that's air-gapped, meaning it's completely isolated from any networks. No internet, no Wi-Fi, nothing. It's supposed to be impossible to get data off that machine without physically accessing it. But with screaming pixels, an attacker could potentially use the screen to send out encoded messages through sound waves.
Wow, so it's like bypassing all those security measures they have in place to protect these really sensitive systems. That's a big deal.
It is, and it highlights why security research is so important. We need to stay ahead of the curve anticipate these kinds of threats, and develop ways to mitigate them.
It's like a constant arms race, right? As soon as someone develops a new technology, someone else is trying to figure out how to exploit it.
Exactly. And that's why it's crucial to have open communication and collaboration between researchers, security experts, and policymakers. We need to be talking to each other, sharing information, working together to make sure these technologies are developed and used responsibly.
It's a reminder that technology isn't just about cool gadgets and innovation. It's about people and how we use these tools to shape our world. And that's something we all need to be thinking about, not just the experts.
I agree. And I think this deep dive into screaming pixels has been a perfect example of that. It's fascinating, it's potentially revolutionary, but it also raises some serious questions.
Questions that we all need to be asking. So thank you all for joining us on this journey of discovery. We've only scratched the surface here, and who knows what other mind-blowing technologies are just around the corner. But hopefully this is giving you a glimpse into just how strange and how exciting the future of technology can be. And we'll be back next time with another deep dive into the weird and wonderful world of cutting-edge research. Stay curious, everyone.